Here's the lecture from section 3.1. This lecture has to do with the introduction to derivatives. So first of all, before we start getting into the nitty-gritty of the mathematics, we might want to ask the question, why are derivatives important? They're important because derivatives are slopes, and slopes in themselves are important. Slopes are rates of change, and rates of change show up in all sorts of really important questions, like how fast is this elevation changing? This is really important for people who are building, people are building roads, people are building houses. How quickly are we producing those cars? Obviously, production has a lot of very interesting and important ideas. How many acres a day are the rainforests being destroyed? Well, there's an environmental thing. So anyway, when we have models of behavior, we can study the derivatives to talk about the rates of change that are inherent in those models. So as we start this question, we might say, well, rates of change, those are slopes. Slopes are trivial. The slopes for this kind of problem is quite easy. In fact, any problem that's in the form of y equals mx plus b has a trivial slope. By inspection, you'll be able to tell, oh yes, this slope is 3. Or maybe by inspection, you'll be able to say, oh yeah, I recognize that this slope is -2. Or even though we may write the linear equation in a more in a different form, you should be able to tell, oh, the coefficient that's on the x squared term is going to be this -2. This slope is still -2. And we recognize in general that slopes can be calculated in the form y equal or m is equal to this y2 minus y1 over x2 minus x1. Sometimes this is referred to as delta y over delta x. Sometimes this is referred to as rise over run. And we do this so that we can calculate the slope of a line given 2 points. So for this example, here's a linear equation given graphically, and we can say, well, no, here I can pick out easily 2 points on this graph. Here's 1 point, that's 1, 1. Here's another point, which is over 0 but down -1. We can see that this run here is of exactly 1 unit. You can see that this rise here is of 2 units, or we could think of this as 1 minus a minus 1. We can think of this as 1 minus 0 for the run, and in doing so we can say, oh, I can see that the slope of that particular line is 2. And that's great. You know, those are easy. We'd like to have those problems all day. But what happens when we're dealing with nonlinear functions? What's happening when we're dealing with a function which the graph is not a straight line, like this parabola? So let's talk about what it means to find an estimate of slope in this situation. And for convenience sake, we're going to look in particular to what is the slope at the point 1, 1. Now what we're saying here is that if I want to find the slope at 1, 1 and it's not a line, we may say, well, what I really want to do is find the slope of the line that's tangent to that point on that to that curve. And one way to do that would be to use a secant line estimation. If I want to find the estimate of the tangent of that point, I might choose a secant line to do that estimate. But of course that begs the question, well, what's a secant line? How are we going to find the estimate of the slope of this blue line? And the answer is, a secant line is a line that's found by putting 2 points on the curve and drawing a line through it. Now, if we wanted to find the estimate of this point, the estimate of the tangent line at 1, 1, and I could draw that line in there, we might say that it's very well estimated by the by the by the line that goes through the point 0, 0 and through the point over 2 up 4. And because we have that formula for slope, we say, oh, this slope is 2, so we can estimate the value of this slope to also be 2. And this process, by going a little bit up below and a little bit above the point that we're trying to, is a pretty good estimate. But I want to show you a method that gives us even better estimates. And it's still using secant lines, but we're going to do it slightly differently. Now, I'm going to still be focusing on this question, what is the slope at this point 1, 1? And I'm still going to use a secant line. But what I'm going to do is I'm going to say, when I make my secant line, I'm going to have 1, 1 be one of the 2 points from my secant line. Now, I could very well say that the second point on the secant line is the point negative 1, 1, and I draw the line through there, and it tells me that the slope is 0, and I'm thinking, well, you know what, that doesn't like a very good estimation at all. I wonder, I'm bringing up this point about using this fixed point. I wonder if we can make this estimate better. Well, first of all, before I get into doing that, I just want to explain what you're seeing on the screen. This A here means that 1 is our fixed point. This H here refers to how close I am to this fixed point. So in this case, I'm negative 2. I'm 2 units below 1. And again, its estimated slope is 0. Well, what would happen if we still keep our fixed point and we started moving the second point closer and closer to that fixed point? Well, it's my statement that we can get better and better estimators of that tangent line slope. And let's give that a try by looking at a demonstration of that using our calculator. So switching over to the calculator, and again, here's where we left off with that picture, and I'm going to start moving my point closer and closer. And so here I am, I've moved an entire unit closer. Now I'm only 1 below A, and what do we see? Oh, that red line looks a lot closer to being an estimate of the tangent line. And of course, what I can do is I can get even closer. Now I'm only half a unit below my fixed point. And indeed, I still say that this is even better estimation of the slope, 1.5. But I can also get even closer. Now I'm only 1/10 of a unit below my fixed point. And I've got an estimated slope of 1.9. And that's a really good estimation. How about I get even closer? What happens when I go to 0? Well, the line disappears, and it says the slope is undefined. Why is that? Well, if I'm 0 points away from A, that means my rise is 0, but also my run is 0. And dividing by 0 gives me an undefined value. If I go just a little bit higher, I go 1/10 above, I've got this estimate, 2.1. Wait, I can go 1/10 of a point below, and I have an estimate of 1.9. Now, what do you think a good estimate of the tangent line slope would be, considering that I'm 1.9 when I'm 1/10 below, and I'm 2.1 when I'm 1/10 above? Well, I'm not going to force you to say that you think that it's 2. I'm going to say, well, what if it got even closer? What happens if I say, So now I'm a tenth of a point below, the slope is 2.1, and now I want to say, what if we start going up by getting really close, and now I can get within 100th of being off. And take a look at the estimate of the slope, 2.01. And what happens at 0? It's still undefined. And what happens at 0.01? Oh, I'm at 1.99. So now this idea that the estimated value of that slope is 2 sounds really, really good. And I could even go up and get even closer. What happens now when I go, and now I'm getting within 1/1000th of the 2 points. The 2 points, you can hardly tell that they're 2 different points, and it estimates the slope at 2. And if I go a thousandth of a unit above, the slope again is estimated to. So we can do this process and we get a really good idea that the tangent line slope is estimated at 2. Now, are we going to do that for every single problem? I don't think so. What we're going to do instead is say, how do we make formal in our mathematics this idea of making h as small as possible, or as close to 0 as possible, without it letting be 0. Okay, and this is a concept that you've already learned, and that concept is called limits. So here's what we're going to do. We're going to define this idea that I can find a derivative, a slope, a tangent line slope, by saying that I'm going to take a constant point and a fixed point, we'll call it A generally, and we'll have some other point, and we're going to say we've gotten bigger by an amount h. So this point here, or this x value here, is a plus h, and therefore my points here are a comma f of a, and this point over here is going to be a plus h comma f of a plus h. And if I want to find the rise, that rise is going to be f of a plus h minus f of a difference in the y values. And my run, I could write it out as a plus h minus a, but you can see that that will just derive to h. And then I'm going to say, what happens when h gets really small? It approaches 0, but does not equal 0. By the way, when we do this, when we talk about h getting infinitesimally close to the point that we're interested in, I'm going to note that what we're getting then is not an estimate. It is the actual slope. When we get infinitesimally close, we get the real slope. Now, I use the word derivative in describing this process. We call this idea a derivative because we are deriving from, or these slopes are coming from some original function. So let's do this problem and let's say, well, what is the slope of something on the curve y equal x cubed? Well, I can say, well, let's say we're interested in this point right here. All right? Now, we might say that if f of x is equal to y, which is equal to x cubed, then f prime at 1 is equal to the limit as h approaches 0 of f of x, or a of a plus h minus f of a over h. Now let's fill in the gaps here. The limit as h approaches 0. What is a if this is the point we're interested in? And the answer is a is 1. So we're looking at f of 1 plus h minus f of 1 all over h. Now, what is f of h plus 1? Well, that's going to be 1 plus h cubed. What is f of 1? Well, if f of x is x cubed, that'd be 1 cubed, and this is all over h. So this is the limit as h approaches 0 of, well, let me just do little Pascal's triangle here. Okay, this expands to 1 plus 3h plus 3h squared plus h cubed minus 1 all over h. And then these ones cancel. Now, can I apply the limit here? Well, if I try to put zeros in everywhere and I get 0 over 0, oh, that doesn't look too good. But maybe there's an algebraic manipulation that we can do to make our lives easier. How about we factor an h out of each of the terms on top? And when we do that, those h's cancel. Now I don't have that 0 divided by 0 problem. I've got something where I can simply apply the limit. Zeros go in for each of these h's, and I get the value 3. So we say that the slope of the f curve at 1 is equal to 3. Let's take a look at that. If I were to draw something that goes over 1 and up 3, over 1 up 3, does it look like I indeed get a tangent line slope? It sure does. Now, there's an alternate way of writing this. Same idea. We can think of our fixed point still as a f of a, and we could think of our point that is sliding and getting ever closer to that point as the point x comma f of x. Now, when we do that, we still end up having a rise, and that rise is f of x minus f of a, and we still have a run, and that run is x minus a, and we can just talk about x getting closer and closer to a. Now, the reason why we have an alternate version that's totally equivalent to what we did earlier is because sometimes the first definition works out well, and then other times this definition works out well from an algebraic standpoint. So, for example, if I'm dealing with this question, I would like to find the line of the slope of the tangent line at this particular location, and this happens to be the root curve. Now, again, I can think of this as being my f of my x value a, and this is the point a f of a, and then this point here is x comma f of x. All right, and I could say, well, I would like to know what if I define f of x as being y, which is the square root of x, then I can say that f prime of 1, which is to say a is equal to 1, is equal to the limit as x gets closer to 1. I'll write it out in their original form, f of x minus f of a over x minus a, or the limit as x approaches 1 of f of x, which is x squared, minus f of 1 over x minus 1. Now, what is f of 1? F of 1 is the value of this curve. Oh, that's what is the square root of 1. That is the square root of 1 minus 1. Now, can I apply the limit right here? Well, if I do so, I get 1 minus 1. It's a divide by 0 error. Cannot apply the limit at this point. But is there an algebraic manipulation that will allow us to solve the problem? Well, let's try the limit as x approaches 1 of the square root of x minus 1 over x minus 1, and let me multiply this by what we call the conjugate of this expression, which is the square root of x plus 1. And again, this is a technique that you may have seen in pre-calculus. I don't know why it's going on the next slide all the time. Alright, now, what happens if I expand that top? Well, I get a difference of squares, and I get x times a square root of x times square root of x, which is x, and I get plus square root of x minus square root of x, and a minus 1 at the bottom, at the back. And then on the bottom, I'm going to just leave this as x minus 1 times the square root of x plus 1. Now, you can see that the square roots of x cancel, leaving me on top x minus 1 over x minus 1 times the square root of x plus 1, and those two cancel, leaving me the limit as x approaches 1 of 1 over the square root of x plus 1. Now when I apply that limit, I don't get a divide by 0 error. I get 1 divided by 1 plus 1. I get 1 half. And then let's see if that makes sense. If I have a run of 2, which takes me all the way out to here. No, a run of 2 would take me to 3. 1 plus 2 is 3. And if I go up 1, does it look like when I draw a line through those 2 points, I get a tangent line there? Oh, it doesn't because I drew it wrong. Try that again. I go over 2 and up 1 is all the way up to here. There we go. If I draw the tangent line through there, that looks like a true tangent line, where the green line is just an estimation. So, when we see polynomials, I'll tend to use the h version of the derivative definition. When I see square roots and when I see fractions, I'll tend to use the a version, or the x minus a version. So now we did that those two examples for specific points. I do want to mention here that we can generalize this for any function, and not just say for a particular point, but just say for any particular x. You'll see that the definition looks exactly the same. And if I do that, I can do something like this. Well, what is f prime of x for x squared? Well, I could say, well, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. But in this case, f of x plus h is x plus h squared, and f of x is x squared. Can I apply the limit at this point? Nah, I got to divide by 0 error. Let's see if we can do some algebraic manipulation. The limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared over 2. Golly, I'm really glad I know my algebra. Expanding that binomial like that. Alright, x squareds cancel. And what does that leave me? Well, that leaves me 2xh plus h squared. Well, you know what I see? I see that in those two terms there's a common h. If I pull the h out of there, I get that. And those h's cancel. And now I can apply the limit and not get a divide by 0 error. When I put in the 0 in for h, I simply get 2x. Now what does that mean? That means that when I have the function, the parabola function here, that if I want to know the slope at that particular point, I could say, well, what is f prime of 0? And I could plug it into there. 2 times 0, and the slope is 0. And indeed, I have a horizontal tangent there. If I want to find out what the slope is at 1, as we found out earlier, I can say it's 2 times 1. And indeed, the slope here appears to be about 2. And what about over here at negative 2? F prime of negative 2 is 2 times negative 2. It's negative 4. And indeed, this looks like a negative 4 slope. Now, other things that you're expected to be able to do with having to do with this idea of a derivative is to be able to say, well, what if I am given the graph of a function? Let's call this the function f. Can I draw its derivative, f prime of x, and say, well, what do we have? Well, hey, over here at negative 1, there appears to be a horizontal slope. So that means on my derivative graph, I've got a slope of 0. You know what? Over here at about, what is that? About 1, well, this is 1. So this is really at negative 1/2. And this is about 1 1 1/4. At 1 1/4, it looks like I have another horizontal or 0 slope. Now, in between here, all these slopes are negative. So maybe what we have here is negative behavior. And over here, I see increasing. All these slopes, all these tangent line slopes are positive. So I think that goes up that way. And over here, all of these slopes are positive as well. So I have positive values of slopes there. And that is an estimate of the graph of f prime simply based on a graph of f. Now, because this is math class, we may have multiple ways of talking about derivatives. I've called the derivative the f prime function, for example, because it's a function. It's a derivative function that comes from a different function. In a similar way that when we did reflections in geometry, the reflection of A is A prime. Another thing that we might be talking about, though, is because this is a rise over run situation, because it's a slope, we may use the notation dy over dx, where dy represents a change in y, like a delta y, and then dx is a change of x. And we'll get into later why we call it dx and dy as compared to calling it delta x and delta y. Lastly, we want the idea of finding, we want a verb form of this notation to say what happens when I go and I take the derivative. I find the derivative of a function. The action of taking a derivative is called d over dx. And we could say in here, I am having the action of taking the derivative of f. And when I do that, I get f prime. So we have a couple different ways to talk about the derivative as a noun. These are both nouns. But this particular thing, we're going to call it the verb, the action of taking the derivative. Okay. Now, we've talked about these generally. Are there any special cases? And there are. Thanks for asking. Here's a special case that we need to consider, and it's the case having to do with absolute value. There's a really, really special point with the absolute value function right here. And we're going to talk about this particular special value on this particular special function. It causes some hiccups in our definition, and let me take you through it. Let's find the slope at this point using secant lines. All right? Now, what happens when I'm looking at values that are less than 0? Let's say this is the point that I have a secant. I'm going to make my secant line slope. And if I draw that secant line, I get a slope of -1. And if I get closer, I get a slope of -1. And if I get closer still and closer still, all of these slopes give estimated values of -1. Now, what happens if I go over to the other side and say, well, how about if I use this for the secant slope? Well, that gives me an estimated slope of 1. And even when I get closer and closer and closer, all of these slopes are equal to -1. So I have a bunch of slopes that are +1 on this side. I have a bunch of slopes that are negative on the other side. What does it mean for the true value of the slope at that point? This is a problem. These two values don't agree. Here's how we're going to handle this problem. We're going to think of these slopes like limits, because when we define the derivatives, they're limits. And we have this idea with limits that the limit for this particular function, let's say, doesn't exist at 0. Why doesn't it exist? Well, we have this idea of a left-handed limit. The left-hand limit of this function is equal to -1. It's -1 all through here. The right-handed limit, as we approach 0 from the positive side, are all 1s. And because these do not agree, we say overall the limit of this function does not exist at 0. The two limits must agree. And again, this is something that you should have covered in pre-calculus. Now, it just so happens that this is exactly the graph of the slopes for the absolute value function. Because we don't have agreement, we are going to say that the derivative, okay, if f of x is equal to our absolute value function, that f prime of 0, I said equal sign, does not exist. More formally, we're going to break it down this way. Every single derivative has a left-handed part and a right-handed part. The left-handed part is the idea that we are approaching our value, but we're doing it with the h values being negative and approaching 0. The right-hand derivative being h values are approaching 0, but from the positive side. And if these two, right-handed and left-handed, don't agree, then we're going to say that at that point where they don't agree, the derivative doesn't exist. These two have to equal each other for the derivative to exist. So when we look at this problem in this manner, we can say, you know what, I think of the absolute value function as a piecewise function. When x is less than 0, you have to take the opposite value. So when I take the absolute value of -3, I say, oh, -3 is less than 0. I'm going to say then that function is going to be the opposite of -3, and I get 3, just like I'm supposed to. When I take the absolute value of 3, I say 3 is greater than 0, so I'm going to just use that definition. When I do the derivatives in this manner, I get a left-handed derivative that says, okay, I am going to find the value of f of x, f of 0 plus h, but h is slightly smaller than 0. It's negative, so I'm going to have to use this definition to fill in the gap. And what happens when I get negative h divided by h and take the limit of that? I get 1. On the right-handed side, I've got this going on, but now h is just barely positive, which means I have to use this definition. The value of f of 0 plus h is just going to be h. And when I take its limit, I get 1. These don't agree, and therefore we say the derivative does not exist. Now, there's another special case having to do with discontinuity. And we're going to do this problem in the same way that we did the absolute value problem. We're going to look at the right-hand and the left-hand derivatives and see what we end up getting. Now, the left-hand derivative for this case is the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Now, in order to do this, I'm going to have to know what f of 1 is. F of 1 is equal to, let's see, 1 cubed. Is that right? 1 is equal to 1, so I'm going to use this definition. It's equal to 1 cubed, which is 1. So this is equal to the limit as h approaches 0 of something minus 1. Well, what's going to be the minus 1? Well, when h is 0 but just, or coming in at 0 but is slightly negative. Oh, I'm sorry. Yeah, slightly negative. This value here is going to be slightly below 1. When I'm slightly below 1, I've got the cube definition from above. So I will again write out my Pascal's triangle. So I can expand that, and I get 1 plus 3h plus 3h squared plus h cubed minus 1 over h. When I do that, my 1's cancel. There's a common h. You'll see this theme coming through loud and clear. Whenever we use the h, there's a common h. So we get 3 plus 3h plus h squared all over h. Cancel out the h's, apply the limit, and I get 3. What happens when I do the right-handed limit? The limit as h approaches 0 from the positive side. Well, I still have 1 plus h minus f of 1 all over h. I still end up saying that f of 1 is equal to 1. See if I can make this a little bit more clear. Now, what is f of 1 plus h? Well, when h is slightly positive, this number is slightly bigger than 1. This is 3 times 1 plus h. And this is the limit as h approaches 0 from the positive side. Bad notation here, left off the negatives over here. And we end up getting 3 plus 3h minus 1 over h, or the limit as h approaches 0 from the positive side of 3h plus 2 over h. Now, no amount of algebraic manipulation is going to get the h out of the bottom there. In fact, if we take a quick look at the graph of this function, I need a graphing page. Oops. I want my current document. I want to create a graphing page, and let's do this so I can see what I'm doing. I just want the handheld, and I want to graph this out, but I'm going to pretend the h's are like x's. So a fraction, and I'm going to say 3x plus 2 divided by x, and I graph that. And what happens as h gets close to 0 from the positive side? You'll see that this function is zooming off towards infinity. This is equal to infinity. Infinity, not 8. Infinity. Or we could say that this limit does not exist. But we already had said that in order for the derivative to exist, these two have to agree. Well, if this doesn't exist, these limits can't agree. Our conclusion is therefore f prime at 1 does not exist. And that's going to happen every single time when we have a discontinuity in our function, like this one is. What do I mean by discontinuity? If I would have graphed this function originally, we would have seen this going up to here, But then over here, because this is at 1, at 3, that's when this function takes off. And we have a closed dot there and an open dot there. There's a discontinuity in this function. And whenever we have a discontinuity, the derivative is not going to exist. So we covered a lot in this lecture. In summary, what do we have? Or what have we found out? Well, first and foremost, we want to remember that derivatives are the slopes derived from a function. That these things are going to be important for us to solving all sorts of problems later on. Okay, we're calculating them using the slope of a secant line. We did a quick demonstration where we went a little bit above and a little bit below the point of interest, but we found that there was a much more powerful way of doing that where we use the limits and keeping one point fixed. That there are some places where the functions won't have derivatives, and those places are going to be places where the right hand and the left hand derivatives and the limits that they come from don't agree. And there's going to be places where we have discontinuities where those right-handed and left-handed limits don't agree. And then lastly, that sometimes we can simply look at the graph of something, and by using increasing and decreasing to determine when slopes are positive and negative, and places where there's horizontal slopes and where the derivatives are going to be 0, that we can make a graph based on those derivatives. And I hope you have a great time working on that homework.